I'm going to do experiments using our rotating table. It's about 1 meter in diameter, and I'm going to roll balls down that little ramp. And when the table's not rotating, the ball will travel straight across. When the table rotates, the camera, which is affixed in the rotating frame, will see the Coriolis deflection of the ball. It deflects off to the right when I move the table in a right-handed sense. Now by hand I'm going to move it to the left, and you'll see it's going to deflect the other way. Now we're going to use the motor on the table to rotate it at a constant rate. And what you'll see is the faster the table rotates, the more Coriolis deflection the ball feels. So at 4 RPM, you see the ball deflects a little bit. Now we'll increase the rotation rate to 8 RPM, and the ball will be deflected more. And it does. It's deflected about twice as much. Lastly, at 12 RPM, the ball's deflected even further to the right of its intended path. In a right-handed system that's rotating counterclockwise, the deflection of the particle is off to its right. Furthermore, we see that the strength of deflection increases with the rapidity of the rotation of the system. The experiment here has blue denser fluid at the North Pole on the right and yellow less dense fluid on the left at the analogy to the equator. You could see the blue denser fluid sinks to the bottom of the fluid layer and spreads out, coating the bottom, and thereby heads from North Pole towards the equator. In contrast, the less dense fluid at the equator floats to the top, coats the top surface, and travels from equator to pole. And this is our analogy for a large-scale overturning atmospheric circulation. You can now see that we have the exact same setup as before, but the whole setup is now placed on our rotating table. We pull up the containers and release the die. And in side view, we see roughly the same overturning circulation. But in top view, we see a significant difference. Now the flows are deflected to the right of their intended path. So they're each hugging one side wall, as we predicted based on the effects of the Coriolis accelerations. You can see we released the die. The blue and yellow each spread out from the corner they're initially in, and they coat each of their respective surfaces. You can see the blue dye reflects off the sidewalls. So there we pulled up the containers. The blue and yellow dye tries to spread out, but instead it's massively deflected off to the right of its intended path. John Cantwell is about to pull the cylinder, releasing the dense, in this case, green dye. The dense stuff, maybe not surprisingly by now, sinks to the bottom and spreads out, coating the bottom of the tank pretty much uniformly. Now we have a rotating experiment. Same deal. The dye does not sink. It does not uniformly coat the bottom. Instead, it forms actually a pair of vortices, and that pair of vortices propagates across the tank as a coherent unit. Very, very different response than in the non-rotating experiment. Here's our tank viewed from above. We've got a bunch of styrofoam floating on the surface of the water. We've got a couple of fans. The fans, when we turn them on, blow the garbage around in a circle. In a non-rotating tank, not surprisingly, the floating stuff follows the wind. Now, when we rotate the tank, we get a different behavior. We'll speed up the rotation rate so this all happens faster and so that we all get dizzy. And you'll see the garbage in time will get deflected in towards the center. And eventually, all this garbage will form a patch relatively close to the center of the tank. This is similar to what's happening in Earth's oceans. It's due again to Coriolis deflection off to the right of the direction of the winds. Now we're going to try to understand gyroscopic phenomena. If it's not spinning, when you let go, it falls over. When you spin it, the gyroscopic forces hold it up and it doesn't fall. Now let's redo that type of experiment using tanks of water. We're going to first do an experiment where I just take a packet of creamer, half and half. This is colder and denser than the water in this tank. And this dense creamer is going to sink. Dense things sink. So this is going to sink through the water, and we're going to see how it does so. And what you see is that the creamer quickly falls through, forming a dense, turbulent plume, hits the bottom, and immediately spreads out. It looks somewhat like an inverted mushroom cloud, because it is. So now, to compare what we saw in the non-rotating tank to a case where there is rotation, we've set up a record player, as you see here, and we've got a comparable tank of water on it, and we've let that tank of water spin up so that all the fluid is moving at the same rate as the record player. So all the fluid mechanics knows about the rotation of the table. And now we're going to do the exact same experiment where we pour in the creamer. And what you see is a different behavior. The fluid this time forms an axialized column. All the fluid motions are aligned with the rotation axis. The fluid isn't falling very fast through the layer, and now that column starts to break up into sub-columns. And it eventually breaks apart into these different units, but all of them are each being held up basically by the Coriolis acceleration. In almost all geophysical fluid dynamical systems, we see swirling flows. These are called vortices. And we see them in Earth's atmosphere, such as hurricanes, and we see massive vortices on Jupiter, Saturn. Almost everywhere we look in geophysical systems, we see these fabulous vortical structures. We're going to do some simple experiments to try to get a first-order feel for how they behave. So for our non-rotating experiment, we've put some potassium permanganate here at the bottom. Now we're adding some blue food coloring, some green food coloring, and some orange food coloring. We're going to flip a little plastic flap there on the left side of the tank, right there, right at 9 p.m. There's the flap being flipped. That builds a vortex. We'll now speed up the speed of the movie so we can see it. And you can see it's strongly three-dimensional. There's tons of turbulence inside there, and it's quickly mixing together all the different colors. And that kind of a strongly three-dimensional, highly turbulent vortex is somewhat comparable to what you see in a hurricane.